How are you ladies doing this morning?
I'm doing good.
Good.
Okay. Looks like it may just be the three of us, and that's okay. Somebody, not one of you, asked a question about a homework problem, so I wanted to talk about that first. And then we could jump into some other stuff. So let me share. Let's see. This is what I'm looking for. So the student in his email asked, when we are looking for the inductance equivalent for the time constant in problem 4, part D, do we short circuit the resistors / ignore them and just focus on the inductors? And that's an odd question, so I'm just going to address what we should be doing, okay? So in problem 4, we can see that that switch closes at t is equal to 0, putting a short circuit in the middle of the screen. Do you guys see that?
Yes.
Great. So this is going to be a natural response style problem then, because that short circuit is effectively making that 5 amp source on the left-hand side of the circuit not be able to affect either of the inductor currents. So what we should observe is that the inductor current I1 is going to flow. Let me figure out how to turn on my pen real quick. In this loop. So it's going to flow down through the 2.5 Henry inductor, come along the bottom path, and then flow up through the short circuit of the switch. And similarly, the inductor current I2 is going to flow around in this path, right? So in both cases, the inductor is going to see that short circuit from the switch, and it's not going to see any other viable path for current to take. So this is still a first order circuit, even though it has multiple inductors in it, because the inductors don't interact with each other once that switch closes. So the time constants for this circuit then, the time constant for an RL circuit is, let's see, tau is equal to L over R, if I'm not mistaken. So for this guy, the time constant for inductor 1 should be 1/2, and the time constant for inductor 2 should be 4 over 20 is 1/5 of a second. So 500 milliseconds and 200 milliseconds. And let's see, for part E, using the results from part A through D, determine an expression for I switch, you'll need to account for both these currents that are going to flow up through the switch, the contributions from the inductor, as well as the contribution from the 5 amp current source. So it should be something like, based on the direction we have, 5 amps minus whatever the initial condition on I1 is, e to the minus 0.5t minus whatever the initial condition on inductor I2 is, e to the minus 0.2t. Make sense?
Yeah.
Cool deal. I mean, I know you guys weren't the ones asking the questions, so, but maybe you had a question and perhaps I have answered it. All right, so did you guys have any questions about any of the other homework problems or anything? I know that I've given you to do those.
No,
You haven't
not
even
yet.
started yet? Okay.
No, I don't either.
Okay, cool deal. Well then, let's stop sharing this. All right, so I posted some lecture notes online with regards to amplifier circuits, because that's what we're going to be talking about for the next several days. Did you guys have a chance to review them at all?
Yeah.
Do you have
Yes.
any? Okay, cool deal. Do you have any questions about them? Hopefully, yes. If not, this is going to be boring and short.
I'm sorry, no.
You don't have any
A
questions?
couple of things with op amps in our other classes.
Okay, yeah, you guys are biomed, so you've actually had probably more experience than the EE students at this point. So it would have been boss if they had shown up. Have you dealt with the practical op amp model at all in your biomed classes?
I don't think so. No, we don't get that detailed into it. We use the triangle model version.
So you're probably using the ideal model then. Okay, so
Yeah.
all right.
Yeah.
All right. Let me pull up the whiteboard and try to do this not too terribly. Share screen. All right. So the model that you ladies are used to using looks something like this. I'm not mistaken, where this is the output voltage pin. This is the, let's see, I'm going to call it VN plus, I guess, for right now. This will be VN minus. And VN plus is for the non-inverting input terminal, and VN minus is for the inverting input terminal. Is that correct? What you guys are used to?
Yes.
All right, can I change the color on this? Gotta be a way to change the color, huh? Maybe not. All right. So in this class, we're also going to have to pay attention to what's going on with the power supply terminals. So I'm going to call this guy VCC plus, the positive power supply terminal, and this guy down here, my pen thingy will write VCC minus, and it'll be the negative power supply terminal, okay? And the reason why the power supply terminals are important, I think I stated it in my lecture notes, is that a real op amp can never actually exceed the power supply voltages. So we're going to run into a situation called saturation distortion. And it's called saturation distortion because an increase in the input signal does not cause a corresponding increase in the output signal. So we get effectively a hysteresis loop. I think you guys are probably familiar with what hysteresis loops are.
I'm not sure.
So
Maybe.
all right, so the saturation distortion that I'm talking about is, let's say that we have an input signal that simply increases linearly. That's my goal here. So this is V n of t, and this is time. And we just have some V n of t is equal to some slope times t. So a 0 DC offset, okay? So if we were to feed this signal into our op amp, in the ideal case, the output would simply be a scaled version of the input. So V out would just be K, some scaling factor, times the N of T. That's what you guys are most likely used to. Now,
Yes.
okay, so if our
Yeah,
power,
we've seen some of that.
okay, so the issue is that if our power supply voltage, say, is at this level, VCC plus, then what we would actually observe is that instead of increasing linearly, our output signal would saturate. So it would stay at, once it reaches the output level, it will stay, or excuse me, once it reaches the level that is the same as the power supply voltage, it stays at that voltage. So it doesn't continue to increase up here, it just stays flat like this. So we're actually clipping off our input signal. And the hysteresis portion of it comes from the fact that it's going to stay there even as we decrease the voltage until we go below this threshold. And we could see a similar effect on the, if we tried to get more negative than the negative power supply voltage. So an operational amplifier then has a limited linear range, where inside the linear range, the output is a scaled version of the input, and outside the linear range, we have saturation distortion, which is this guy right here. And this is going to come into play an awful lot in our first few amplifier examples. So I'd be willing to bet that since you've been using the ideal op-amp model, you've probably also been limiting your experience to what are called negative feedback op-amp models, or negative feedback op-amp circuits. So let's see, how can I erase some of this stuff? So this guy that I've drawn over here on the left would be considered an open loop op-amp circuit. And it is an open loop circuit because there is no conductive path formed between the output and either of the inputs, okay? What you're probably most familiar with something like this, where the position of my inverting and non-inverting input terminals, but that's okay. Probably have a resistor of some sort here. So you're probably familiar, and obviously there would be signals connected and things like that, but this is an example of a negative feedback circuit because there is a conductive path between the inverting input terminal, or the negative terminal, and the output terminal. And negative feedback amplifiers are inherently extraordinarily stable. So this is why the overwhelming majority of circuits that we'll deal with will be of this type. So this is negative feedback. And there's also positive feedback op-amp circuits. I guess I should flip those, but it'll be okay. Where the feedback path is from the non-inverting input terminal to the output. And these type of circuits are inherently unstable, which may seem like a bad thing, but it's great if you want to make an oscillator or something like that. So this is positive feedback. So in this class, we actually start by looking at the behavior of open loop op-amp circuits, and then go towards positive feedback circuits because their behavior is extraordinarily similar before finally settling on the behavior of negative feedback circuits. And the notes that I've posted, so I think the one that's called Lecture 2 primarily focuses on open loop op-amps. The one that says Lecture 3 is positive feedback op-amps, and then Lecture 4 introduces negative feedback op-amps. The ideal op-amp rules that we used in Circuits 1, and you've probably used in your biomed classes, are actually only valid for circuits, and we'll explore why that is in this class. Before we jump ahead and start playing around with stuff, have you, I guess, does the resistor placement make sense to you for negative feedback versus positive feedback versus open loop?
Yes. Taylor just texted us and said that her screen says she's still waiting for the host.
I don't know how that's possible because I'm in here.
I don't.
And you guys are also in here.
Yeah. I do not know.
Let me see something. Because I don't think I have this set up to, like it should be, you just can't start the meet, or you can't join until I'm in, but after that, I shouldn't have to let you in or anything. Let's see. I don't see anybody on the participants list waiting to get in, so could you text her back to just try to close the meeting and try to rejoin or something? All right, well, while that's going on, I'm gonna erase some of this stuff. All right, so this is a pretty simple open loop op-amp circuit. And we are not going to analyze it using the ideal op-amp rules because it's an open loop circuit, so the ideal op-amp rules don't really apply. Instead, we're going to analyze it using the practical op-amp model. So the practical op-amp model is in your notes, but I will redraw it here. So we have an input resistance. And apparently I'm going to need to wear one of those silly gloves so that my hand doesn't make random marks on the screen. Let's see, which means I'll have to buy one. So this terminal is for the non-inverting input terminal, and this terminal down here is for the inverting input terminal. This guy is what's called our input resistance, Rn. And we have a differential voltage, Vd, that is simply the voltage drop over that input resistance. And then over here, on our output side, we have a dependent voltage source, AV multiplied by VD. Output resistance, and then this is our ground. Alrighty, so this is our practical op-amp model. Now we need to adapt our actual circuit to this. So one thing that I should point out is that all of these voltages represented in the left-hand figure are with respect to ground. So the 2 volt that is applied at the inverting input terminal is with respect to ground, so that would be the same as me just putting a 2 volt source right here. And then my Vn is with respect to ground. So there's where my input voltage would lie. This is me redrawing this guy. So in the notes, it says that an op-amp can be classified by 3 parameters: the input resistance, the output resistance, and the voltage gain, AV. So in this example, let's give a typical value for the input resistance. So let's say that Rn is 1 mega ohm. And let's say R out is 25 ohms. And that our voltage gain, AV, is going to be 100,000. So that would be 10 to the 5 volts per volt. And I want to figure out how the output of this system behaves as we swing the input voltage from 0 volts to 5 volts. Okay. So my goal here is we're going to plot V out versus V in, okay? So let's start with something fairly straightforward. If Vn were 1 volt, or 0 volts, let's start there. Dang it. I gotta get used to drawing on this thing. What would our output voltage be? Do you guys have any idea how we might go about analyzing this circuit?
The output would be just A times your your volt VD.
Okay, yeah.
Yeah.
So the output voltage is always just going to be AV times VD. You're 100% correct there. Since we have an open circuit at the output, no current's going to flow. We're going to see no voltage drop over our resistor V out. So R out. So V out is exactly equal to AV times VD. That's great. So if Vn is 0 volts, what's VD?
0. Wait, no.
So VD is defined as the voltage present at the non-inverting terminal minus the voltage present at the inverting terminal, right? Which would be 0 minus 2 volts is -2.
So -2.
Okay. Actually, I need to make a quick change here because I'm not going to be able to see everything I want to see. Draw. That should work because I need to allow for negative output voltage. All right, so we have determined that VD is -2 volts. -2 times 100,000 means that our output voltage should be -200,000 volts. Is the math correct? Let's start there.
Yes.
Yeah. So it should be -200,000 volts, but if we apply the saturation distortion, meaning that we are limiting our output voltage, saying it can be no more negative than VCC minus, what is our actual output voltage going to be then? So VCC minus is this guy right here.
Right.
So we're going to saturate to that value. So anytime our output voltage is greater than -10 volts, or anytime our output voltage is mathematically greater than -10 volts, practically it will saturate to -10
It's gonna be
volts.
-10.
So it's not going to exceed the power supply voltage. So it's going to be somewhere down here at, let's say, -10. Now, dang it. What happens if Vn were 1 volt?
Be -1.
So VD would be -1.
Your VD, yeah.
So V out mathematically should be -100,000 volts, which is more negative than -10 volts. So what's the output voltage?
It would still just be -10.
-10, that's right. So it stands to reason that for all points between 0 and 1 volts for Vn, the output voltage is going to stay at -10. So what about when Vn is equal to 2 volts?
You got 0.
Right, so VD is 0, so V out is 0. And since V out is mathematically between our power supply voltages, our output voltage should actually be 0. So this begs the question of then, well, what's going on between 1 volt, Vn is equal to 1 volt and Vn is equal to 2 volts. So, dang it.
I think we may have touched on this in our other classes. It's a sinusoid, isn't it? Or
No.
no.
So let's
Wait.
look at Vn is 1.99 volts. So what's VD in this case?
-0.01.
Okay. And if I multiply that by my voltage gain, what's my output voltage?
Oh, my calculator's dead.
So we have VD is -0.01 volts, correct? We multiply that by 10 to the 5. And we get -1,000. Is that correct?
Yeah, so it's still -10.
So it's still -10. So really, really close. It's going to be still at -10. If we did Vn is equal to 1.999 volts, what's going to happen? We're going to have
So-
-0.001.
Same thing. So is it just going to be like a step function?
Negative 100. So effectively, yeah. So what it's going to look like, there is going to be a linear slope to it. The problem is that the linear range that we have here is going to be so incredibly tiny. It's going to be on the order of a few microvolts of swing where it's actually increasing linearly, that it's going to look like it instantaneously jumps up to 0. So it's going to look like it's a step function, even though there is technically a very, very small linear range to deal with. And we can see that if our differential voltage VD were just slightly higher than 0, so if VN were, say, 2.001 volts, what would we expect our output to be?
I'm sorry, can you repeat that?
Sure. If VN were 2.001 volts, what would we expect our output voltage to be?
Oh, positive 10.
Right. So it's going to swing up. So it's going to...
Same thing on the other side.
Yep. So it's going to jump up to positive 10. And then continue like so. So this particular type of circuit is called a non-inverting comparator, okay? It is a non-inverting comparator because what it's doing is it's comparing the input signal to a reference voltage. In this case, our reference voltage is this 2 volts. Anytime the input voltage is less than our reference voltage, the output is VCC minus, and anytime our input voltage is greater than our reference voltage, the output voltage is VCC plus. So this is literally just comparing the signal strengths and then giving us what's effectively a digital output. It's either high or low. So we could use that to create a digital to analog, or excuse me, an analog to digital converter. So what if I wanted to design a circuit? Erase some of this stuff. Using a comparator. We'll keep these assumptions. Rn is 1 mega ohm, R out is 25 ohms, and our voltage gain is somewhere around 100,000 because that's typical for a practical op amp. And our design constraints are as follows. So we want V out is equal to 5 volts for Vn less than 2 volts. And we want V out is equal to 0 volts. Sorry, Vn greater than 2 volts. Dang it. Driving me insane. Silly tablet. For Vn less than 2 volts. So these are my design constraints. This is going to be a simple analog to digital converter. If our input signal exceeds 2 volts, we're going to output a digital high of 5 volts. And if our input is less than 2 volts, we're going to output a digital low, which is 0 volts. So using a comparator, how can I make this happen? What voltages do I need to put where?
So you need your reference voltage. So it would just similar to how we did it the last one.
Comparing things to 2 volts, right? I'm comparing my input signal to a voltage of 2 volts. So 2 volts should be my reference signal.
Yeah.
All right. So if I want V out to be 5 volts when V in is greater than 2 volts, what does that mean for one of my power supply voltages?
Should be +5.
Okay. And should VCC plus or VCC minus be +5?
You're plus.
Okay. Now, what about my second statement? So right now we do have it set up to where if V in is greater than 2 volts, our output will be 5. What about the second condition? V out needs to be 0 volts for V in is less than 2 volts.
Would you just put 0 for
Yeah.
your VAC? It's just ground.
Right. Ground is the same as 0. Or
Right.
0 volts. Yeah. So we have successfully designed a simple analog to digital converter.
Beautiful.
Nothing wild or crazy about it. We know what the op-amp, open loop op-amp configuration is capable of, and now applied our design criteria the desired output. We're going to have lots of design problems, and it's really going to follow that steps. What can our op-amp do? Some of the later ones will be a little bit more difficult in as much as you'll have to think, all right, I need to perform this mathematical function. So which op-amp configuration can do that? But beyond that, it's just this step-by-step process of what pieces do I put where. What if I had set my design constraints to what my original inequality signs looked like? So to be clear, the n greater, let's see, so less than 2, greater than 0. So what could I do here?
Would it just be you flip the power supplies?
No. Instead of flipping the power supplies, I would actually flip the pin where I put my input voltage and where I put my reference voltage. So let's talk about what does that. All right. So let's see. So this would be.
Oh, because the power supplies, you gotta have the positive and negative sides.
Right. So let's see, erase.
Does that just make it a non-inverting?
So the last one was a non-inverting comparator. So this one's going to be an inverting comparator. Okay. Right. So if I sorry, what was that?
I said yes.
So if the input signal is on the non-inverting pin, we have a non-inverting comparator. And if the input signal is on the inverting pin, we have an inverting comparator. So if I redrew this, using my practical op-amp model, this is my non-inverting, my non-inverting voltage. This is my inverting voltage. This is Rn. So let's see. Plus minus Vref. Out. D. I did the mistake again. So here's V in, here's V out. All right. So if let's say for argument's sake again, vref, I don't know why this is not drawing that part of the 2.
Your reference is still 2.
Yeah. So if my reference voltage were still 2, and this guy is Vn, I think I'm going to have to learn to draw in OneNote because this whiteboard thing is driving me nuts. Only using one color and can't scroll as far as I know and all that kind of good stuff. Anyway, let's see. Vn. Let's start with Vn is equal to 0 volts. So Vd, the definition for our differential voltage, literally never changes. It's always the voltage at the non-inverting terminal minus the voltage at the inverting terminal. So in this case, Vd would be V reference minus Vn, which is 2, which means our output voltage mathematically should be 200,000. 200,000 is greater than the 5 volts that we have applied. So it should be at positive 5, or whatever VCC plus is, right?
Mm-hmm.
At 1 volt, Vd is 1, or for Vn is 1 volt, Vd is 1. So 100,000 is still greater than 5 volts. So it's going to stay there. 2, 3, 4, 5. At 2 volts, it's going to drop down to 0, and then it's effectively going to stay 0. So we have an inverting comparator because when the input signal is low, the output signal goes high, and when the input signal is higher than the reference, the output signal goes low.
Mm-hmm.
So, all right, so one more example problem, and then I think that'll be enough potential harassment for you guys today, or learning, whatever you want to call it.
Well, a little bit of both. A lot of learning, a little bit of harassment.
That's good. So we're going to revisit our first design problem there. This might require a little bit more space, so I'll redraw this. All right, let's see. So we're going to have the exact same design constraints, but this time, so let's say V out is equal to 5 volts for V in greater than 2 volts, and V out is equal to 0 volts for V in less than 2 volts, okay? That's all the same. The issue that I'm going to say is that we don't have access to a 2-volt source, but we do have access to resistors. So how could we form a resistor biasing network to give us a reference voltage of 2 volts?
Is this where you're going to start using the feedback and source resistors?
So actually, no, not in this case.
Okay.
All right, so let's start with our power supply voltages, right? We know for sure that VCC minus should be 0 volts, right?
Mm-hmm.
So I'm going to have this as a ground rail. And we know that VCC plus should be 5 volts, right? Our input voltage, Vin, is still going to be applied to the inverting terminal, the non-inverting terminal, because we want a non-inverting comparator. But what we're going to do now is we're going to use a simple voltage divider network. So we're going to put one resistor here, and another resistor here. And then we need to give these resistors values such that the voltage at this node, which is V reference, is 2 volts. Does that make sense at all?
Yes.
Yes.
Okay, so do you guys remember how voltage divider circuits work at all from Circuits 1?
That's a good question.
Or even Engineering 120. So we have something like this. We have 5 volts, a resistor, 2 volts here, another resistor, and then here's our ground, right? This is how all of your sensor outputs worked in Circuits 1. So let's just say, for argument's sake, this guy is a 10 kilo ohm resistor. Let's call this guy R2. This guy up here is R1, and that's the resistor value we want to find. So I'm just making a generic assumption that I'm going to set R2 to be equal to 10K and then use that to solve for what R1 has to be. So the output voltage of a voltage divider network, V out, is equal to our source voltage multiplied by, well, actually, let me specify here. No, this will work. R2 divided by R1 plus R2, where I'm defining my output voltage to be the voltage difference from this pin to ground, which is the same as the voltage drop over resistor R2. So hopefully this equation looks vaguely familiar. Alrighty, so if we want V out to be 2 volts, and we know that VS is 5 volts, then V out over VS has a ratio of 2 to 5. Is that correct?
Yeah.
So that means that R2 over R1 plus R2 must also have a ratio of 2 to 5, using just simple algebra.
Yeah.
All right, so if R2 is 10 kilo ohms, what's R1 have to be?
Well, 4,000?
So 2/5 is equal to 10K over R1.
Oh, my bad. Opposite. 15,000.
There we go. So if this guy is a 15K resistor and this guy is a 10K resistor, then our reference voltage will be set to 2 volts and we won't have to come up with some 2 volt source, because 2 volts isn't something that's used regularly, right? You could get 1.5 volts from a battery. 3.3 volts is a common output from a microprocessor, as is 5 volts. But 2 volts is kind of an odd duck. But we don't have to bring in a whole different power supply, we can actually use simple resistor networks to create any bias condition we would want, as long as that bias voltage is between the power supply voltages. So, all right. I think that's all I have to talk about today. Do you guys have any other questions about anything?
No.
Well, I actually have one question. Would this lecture be posted on YouTube?
Yes. So I'm literally recording all of this, and it'll be up. And yeah, so all of the issue this weekend. My goal is to actually pre-record. Hold on, it says my internet connection is unstable.
Yeah, I kind of zoned out for a bit. I couldn't hear anything of that.
Okay. So what I was going to say, my goal is to actually have a video lecture pre-recorded for you guys to watch before we actually have this session where I answer questions and we work some example problems and some stuff like that. But I ran into an issue this past weekend and I had to go buy a new car. So I didn't have time to go record stuff.
Okay, yeah. I also had like some problem trying to get into Zoom earlier. It just wouldn't load.
Yeah, I don't know what was going on there. Apparently a couple of people were having that issue, saying it was waiting on the host or something like that. But
Yeah,
I
it
was
said you.
was two students, so I couldn't begin to tell you what was up with that. Other than the weather here on campus is kind of crappy. So I don't know. We'll just do what we have to do while Tropical Storm Cristobal is messing everything up.
Okay, I actually did have a couple questions about the homework, but I guess I could just like email you about it or something.
No, we can. I mean, we still have, let's see, 15 plus 8, 23 minutes left of class.
Oh, okay.
I'm happy to continue answering questions for at least the next 23 minutes.
Yeah. There was a question actually. Let's see. I think it was like it was trying to find the equivalent resistance for like number 1 part C, I think.
All right, let's see. Share screen.
Because I kept getting 6.25 even though it's supposed to be 10.
So for part 1, or problem 1, you said.
Problem 1 part C.
All right, determine. All right, so we're determining the equivalent resistance seen there. All right, so we're looking at a dead network, which means this voltage source here should be a short circuit.
Mm-hmm.
This voltage source is short, and then this 5 amp source should be an open circuit, right?
Okay.
So this 20 and this 20 are going to form a 10 ohm resistor.
Mm-hmm.
Let's see. So that's going to look like 10, 10, 10, 10, 10. Like so, right? That's short. The issue that we're running into there is that so like this 10 ohm resistor on the left-hand side isn't in series or in parallel with anything. Like you would have to use a delta Y transformation.
A delta Y transformation.
Yeah, which you obviously don't know how to do, so that is okay. I can post some notes on that. Let's see.
Yeah, because when I was working this out, this would have only worked if only one of the 10 was gone.
Right, yeah. So I will throw some notes up about delta Y transformations, and that will help you figure out how to do that. So there's I know that it doesn't remotely look like a Y-connected network, but there is a Y-connected network down here on the bottom. And you can make it look like a delta-connected network, which would effectively put these two 10 ohm resistors in series, and it would put that combination in parallel with something else, in parallel with something else. So I'll make some notes on a delta Y transformation and upload them today. Let me put it on my to-do list right now before I forget about it. And I may actually use this resistor network as an example problem so that I can walk you through the steps specifically on how to break it down, because it's going to seem a little bit awkward at first. We are lucky in as much as all the resistor values have the same thing, so it's not going to be that horrifying, but it's going to look a little weird. So I will happily walk you through that.
Okay.
Yeah. All right. Did you have any other homework questions?
Actually, low-key, I think that might have been the only question I had. Well, I mean, would you have any more tutorial videos to show for LT how to use LT Spice with the programming, or is that like something that we'd have to figure out on our own?
So a little bit of both. The LT Spice stuff for ABET purposes is a lifelong learning metric, which means that you guys are supposed to kind of teach yourselves to some extent. That being said, I do have, like, I am willing to help you. So like, which problem are you trying to apply LT, or are you just talking about in general?
I was trying to apply it with the what is it? Number, it could be number 3 or number 2, I don't remember, but I was trying to use the dependent sources.
Okay, so for the dependent sources, in LT Spice, they are called behavioral sources. So for a dependent voltage source, you type in BV, and for a dependent current source, you type in BI.
And how would you
do? It's going to give you an element where you can literally just type in an equation that governs how it works. So like if we looked at problem 3 here, and let's just say I defined this as node A. Oh, because it is node A, that works. And this guy is node C. Your equation for this guy right here would be 2 VA minus VC, because you can't, LT Spice doesn't, it only takes currents. I'm trying to think of the best way. It uses nodal analysis for everything. So when you want the voltage drop over a particular component, you would need to specify both nodes. And then for this guy right here, 0.1 IY, let's just say, for instance, that this was resistor R3. So this guy would look like 0.1 times I R3. Because and currents are defined through components, not between node points. It's just, it takes some time to get used to the quirks of LT Spice. But if you're using the behavioral voltage sources and the behavioral current sources, this should be pretty straightforward.
Okay.
And you can use the label network command to actually label this node as VA, this node as VC, and this node as VB or whatever to make your life a little bit easier. So for instance, the Thevenin voltage would be VA minus VB. Yeah. Oh, well, but you don't need the Thevenin voltage because you're calculating the resistance directly. Okay. Yeah.
Okay. And would there also be like a like an answer or solution sheet posted like after the homework is due?
I'm not sure about that. The reason why I'm hesitant to do that is because if I do that, then there is a distinct possibility that that information would get disseminated to future classes, which means I could never reuse these homework sets again.
Okay.
So I'm not sure.
Okay.
Yeah, I'm not outright saying no. I'm just saying I'm not sure. I will take it into consideration.
Okay. Let's see. I think that might have been all the questions that I had.
Alrighty. Okie dokie. Well, if you have any other questions, feel free to shoot me an email, or we can talk about them on, I guess, tomorrow. I'm going to post a homework assignment for open loop op-amp configurations and all that kind of stuff, probably in the next couple of minutes. It'll be due 1 week from today. I believe that's what I'm going to go with, is just make everything due a week later so that there's plenty of time to ask questions and figure stuff out. Sound good?
Yes, sir.
All righty. Well, unless anybody has anything else, I will catch you all tomorrow morning.
All right.
All right.